Okay, so before we start with the first question, I did want to say that today and for future homework sessions where there will be Python questions, we are going to have a separate Python session that is 7 to 8 p.m. typically after this session, and there will be information about it on Piazza on the weekly posts. So today in the first hour of the session, or from 6 to 7, we're going to go over the non-Python questions. And then there will be a more drop-in session afterwards where you can ask questions about the Python related questions, anything about running the script or something similar. That is all, and we can get started.
All right, I will start sharing my screen for question 1. So for question 1, we are given the van der Waals energy equation, and we are asked to derive an expression for van der Waals force on one atom, starting from the energy equation given. So by definition, we know that the potential energy is defined by the work done in moving an atom from infinity to its present position where a distance is r. So the potential energy is basically the negative integration of infinity to r of force. And then if we rearrange it, we'll see that force is basically the negative derivative of potential energy. Negative derivative of potential energy with respect to distance. Since we have the van der Waals energy equation here, we just have to derive it by distance, and that's going to give you the force equation on one atom. And you can see that in this equation, we have multiple r minimum over r, and r minimum over r. So you can probably just use a substitution rule to solve for its derivative. And it's the same for question 2. It's just asking for the electrostatic force on one atom. And the electrostatic force will be equal to the negative electrostatic energy. Derive it with respect to distance. That's for 1 and 2, which should be relatively straightforward. And then for 3, we're asked to calculate the value of the dielectric constant, given that the van der Waals repulsion and the electrostatic attraction are balanced at the optimal distance for the ion pair at 2.2 Armstrong. So basically, we know that the absolute value of F electrostatic force, electrostatic attraction, should be equal to the absolute value of van der Waals force. And to be exact, they should be equal in magnitude, but opposite in direction. And basically, you just need to plug in all the constants into the force equation that you get from the first two questions. And we know that the little r is 2.2 Armstrong. Then the r minimum is, let's see, the r minimum is 2.9 Armstrong. And then the stabilization energy, or the Will depth is 1 kilojoule per mole. Just need to plug in all of these constants into the force equations that you get from question 1 and 2. And that will give you a dielectric constant, because the dielectric constant basically the only unknown in the equation. And then you need to decide whether this is for water or for interior of a protein or vacuum. And usually the dielectric constant in water is around 80. And in vacuum is 1. And in the interior of protein is around 2. So this should be helpful for helping you decide whether this dielectric constant is in water, vacuum, or in protein. And that's pretty much for question 1. Are there any questions?
For the third part, could you just set the energies equal to each other and then plug in everything?
I don't think so, because if you look at here, the energy shouldn't be equal. The energy shouldn't be equal, but the derivative of the energy in terms of force will be equal, because at the optimal distance, the force are balanced.
Okay, thank you.
Yeah. The absolute value of the force are equal, to be exact. All right, I'm gonna stop sharing my screen if there are no more questions.
Okay, so I will be going over question 2. So question 2 concerns the bond energy of a covalent bond at various internuclear distances. So let's see. So in this diagram, this function in black is the actual energy of a covalent bond. And then this one in blue is the energy that is approximated by Hooke's law. And we're given Hooke's law right here. So as we can see by looking at this diagram, the energy is 0 kilojoules per mole at an interatomic distance that's equal to R naught. And R naught is the equilibrium bond length or the optimal bond length. Then at distances less than R naught, the energy is going to be greater than 0 because there's a repulsive force between the atoms that are too close together. And then at distances greater than R naught, the potential energy is also positive and increasing because of an attractive force between the atoms. And this is until the distance becomes too large and the covalent bond breaks. And at this point, the energy levels out to a value that is equivalent to the dissociation energy of this covalent bond. So the Hooke's law approximation for the energy of a covalent bond only works at certain values, as we'll see in this question. So in the first part of the question, this asks, what are the units of K if we are given the remaining units? So essentially what we have to do is rearrange the units. So we're given that U of R, which is the potential energy, is in kilojoules per mole. Actually, first, let me just rewrite this equation. K times R minus R naught squared. So U of R, we're given is in kilojoules per mole. This is equal to K. R and R naught are both in angstroms. So kilojoules per mole is equal to K, whatever units those are, times angstrom squared. Basically, we can just solve for K, and then we get that the units of K are kilojoules per mole angstrom squared. So these are the units of K. Then in part 2, we're asked under what conditions is Hooke's law a reasonable description of the energy of a covalent bond? So first of all, Hooke's law is typically the function that describes the potential energy of a spring that can be compressed or stretched by some distance. So essentially we're asking, at which values does a covalent bond's energy behave like that of a spring? For this, we can look again at this graph over here. And again, this graph has the actual energy of a covalent bond as well as the energy that is approximated by Hooke's law. So R naught, as a reminder, is the equilibrium or optimal bond length. And at this distance, the energy, both the actual energy that we can see, as well as the energy that's approximated by Hooke's law, are both equal to 0. And this is because there's no net attractive or repulsive force acting on the atoms at this particular distance. So at slight digressions from R naught in either direction, we can also see that Hooke's law approximates the actual energy pretty well. However, we can now look at regions where Hooke's law and the actual energy are different. And so this is where they don't overlap. So this is at greater distances. So if the atoms are brought further apart, that means that the covalent bond would break, and there's no force between the atoms. And so the bond energy stays a constant value, again, equal to the dissociation energy value. So Hooke's law only theoretically considers a spring that doesn't break. So no matter how far you stretch it apart, it's not going to break. But that's not the case for a covalent bond. So for conditions in which a covalent bond is broken, these are the conditions under which Hooke's law is not a good approximation of bond energy. So are there any questions on these first two parts? Okay, we'll move on to part 3. So part 3 gives us the standard free energy change of ATP hydrolysis, which is the energy that's released when a mole of ATP is hydrolyzed, and this can be coupled to power mechanical work. And the value is 35 kilojoules per mole released. Excuse me. So now we need to know whether the energy released by 1 molecule of ATP is enough to stretch a covalent bond by 0.2 angstroms from the equilibrium bond length. So first, we need to calculate the energy that's required to stretch a covalent bond at this distance. So this energy, okay, so first of all, we can use Hooke's law approximation since 0.2 angstroms is relatively a small displacement from the equilibrium distance. So we can calculate using Hooke's law. So now we can say that delta U, which is the change in energy that is required to stretch a covalent bond this distance, is equal to the final energy at this distance. So basically on this graph, this would be like any final energy value, 0.2 angstroms minus an initial value. And so this would basically, since we're using Hooke's law, that would be equal to K times R minus R naught, which is the distance that we're stretching the bond squared, minus initial value, which is just going to stay at the equilibrium bond length. So the initial value is just R naught minus R naught squared. So this is, since R naught minus R naught is 0, this entire term is 0. So essentially we're just calculating K times R minus R naught squared. And K, the value of K we're given is 200. And the units that we have solved in part 1 are kilojoules per mole angstrom squared. So mole angstrom squared. And then R minus R naught is the distance that we're stretching the covalent bond. And so that we are given is 0.2 angstroms, and that's what we're trying to calculate. So units are eventually going to cancel out, and then we get a value that is in the units of kilojoules per mole. So since the energy of ATP hydrolysis is also given to us in kilojoules per mole, we can directly compare these energies, and we don't have to calculate the per molecule energy of either of them. And so then since this value that we get turns out to be less than the total energy released by ATP hydrolysis, that means that a molecule of ATP is sufficient to stretch the covalent bond this distance. Okay. And then in part 4, now instead of the energy, we now need to calculate the force required to stretch a covalent bond 0.2 angstroms. So first of all, can someone tell me just the relationship between force and energy? Yes. So basically what I am trying to get at is that force is the derivative of energy. So energy, basically this equation, that U of R, which is the potential energy, is the negative integral of F of R dr. And so I am just deriving the force equation from this. That's not really necessary to do, but basically this equation for force would turn out to be that F of R is equal to negative du over dr. And then since we're using Hooke's law again, which I will rewrite right here, okay, R minus R naught squared. So the force would be the derivative of this, which would just be negative 2k R minus R naught. And so now we can we can just plug in values into this force equation. And so that would give us negative 2 times K, which is again 200 kilojoules per mole angstrom squared. And we know that R minus R naught, again, since we're stretching the covalent bond, 0.2 angstroms is going to be 0.2 angstrom. And this is going to give us, I'm just going to give the value of minus 80 kilojoules per mole angstrom. And then what we need to do is convert this into units of newtons. So the reason that we want to convert to newtons is so that we can compare it to the force that is exerted by a protein motor, which we're given is 100 piconewtons. So we can do this conversion. So negative 80 kilojoule per mole angstrom, convert kilojoules to joules. And then convert angstroms to meters. I'm just giving that here. So 10 to the 10. And then finally, since we are given the force per molecule of this protein motor, we also want a per molecule instead of per mole value. So 1 mole is equal to 6.022 times 10 to the 23rd molecules. And so that is now going to give us a value of force in joules per meter or newtons. And then we can convert this into piconewtons, compare it to the force that we're given here, 100 piconewtons. And so since this value that we get, it should be greater than 100 piconewtons. And that is why the force exerted by one molecular motor is not enough. All right, are there any questions on part 3 and 4?
Does the negative not matter in that case?
Yes, technically, since we're only considering the magnitude of force, the negative would not matter, yeah. Okay, and then finally, part 5. So part 5 basically asks, why can't protein motors be designed to exert forces much greater than about 100 piconewtons? So essentially this is asking, what are the structural constraints on protein motors? So as an example here, I've provided a typical motor protein, kinesin, and basically the mechanism that it uses to couple ATP to driving mechanical work. So here, ATP binds in this pocket on the protein, and when an ATP is bound, it forms intermolecular interactions with this pink domain of the protein. And then when ATP is hydrolyzed, it releases these interactions. So the intermolecular interactions break and the domain relaxes in a different conformation. So overall, this cycle of conformational changes drives the kinesin motor in a single direction. So we know from part 3, this one, so we know from part 3 that ATP hydrolysis does release a significant amount of energy. So why then, based on this mechanism, which is just an example, what do you think are the structural limitations that might prevent the molecular motors from exerting stronger forces? Anyone can type it or shout it out. So not enough binding sites. So Austin said not enough binding sites, which might be a particular reason, or like a probable reason. Basically, for the sake of time, like what I'm trying to get at here is that exerting forces would require a conformational change between domains. So most proteins are more structurally rigid and aren't able to undergo that many conformational changes because in their folded state, they're held together by non-covalent, weaker intermolecular forces. So if they were to use more energy and exert a stronger force, these intermolecular forces would be broken and the protein would unfold before it's able to break stronger covalent bonds. So basically, proteins have high structural rigidity, and this is due to their being held together by weak intermolecular forces that would prevent them from exerting strong forces. Are there any questions about this?
Wouldn't weak intermolecular forces mean it's not rigid?
So, I think the weak intermolecular forces in this case are holding the domains together in the first place. So I guess you're right that it does add some degree of flexibility between the domains, but to hold the domains together, they still have weak interactions, at least compared to covalent bond interactions.
So
Yes.
just clarifying question. So I don't know if I understood this correctly, but do you mean that if proteins were to exert a greater force, then like the structural rigidity that's borne by like the weaker forces, like that gets disturbed? Is that what it's about? Or
Yeah, so basically if they were able to use, or I guess the reason that they're not able to use stronger forces, like exert stronger forces in the first place, is that if they were to use more energy to exert these stronger forces, then that would be prevented by the structural rigidity of the protein itself.
okay, thank you.
Best way, but yeah.
So if they did exert more energy, since they're held by weak IMFs, they would probably denate, like unfold. So then they
Yeah,
can't.
yeah.
Okay.
Yes, yes, that's what I was trying to say. Yeah. Thanks. Okay, so we can move on. Took a while.
Okay, I will be presenting question 3. Let me just get my camera working correctly. Okay, you should be able to see my clipboard now. Okay. Yes, so question 3 is a question that for practicing the calculations and intuition behind a lot of the common probability questions that you'll be encountering. The first one is about cis and trans bonds, where you have essentially 8 bonds that can be either in the cis or trans conformation. And you are told that they're of equal likelihood. So this means that there's no energy difference between them. And that means we can pretty much ignore energy for now as we go through the probability. So when you are asked for the relative probability, PA over PB, this means that you will look at the multiplicity of the states instead of the energy of the states. So now the probability is simply multiplicity of A over multiplicity of B. To find these, you have to determine how many microstates there are in each in state A and state B. So for state A, you have 6 trans bonds, 2 cis bonds. So you can either have a C and a C, or you can have any combination, and the rest will be T's. But you can have any combination of C, 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 at any of these two. So you have 8 possible spots where you choose 2. And that will be the number of multiplicities, because you have 8 spots, you choose 2 to be C, and the rest will always be T. This is equivalent to saying A choose 6, where you choose 6 places for the T's, and the rest will be C. And then similar for state B, you'll just have A choose 4, where you choose 4 spots to be either cis, or you choose the 4 spots to be trans, and the rest will be filled in. And then when you calculate these and put them over each other, you'll get the relative probability. And that will be this for part A. And then for part B, you're asked about the difference in entropy. And you're given that the statistical definition of entropy is here. When you're asked for the difference of entropy, you just take SB minus SA, and then you'll have KB factored out, ln of the multiplicity of B minus ln of the multiplicity of A. And from the logarithmic properties, you can essentially get this equation. And now they do ask you for the entropy in units of joules per mole Kelvin. And this KB term is in joules per Kelvin. So you will need to convert this to R to get joules per mole Kelvin. And when you do those calculations, you should get your answer. So for part 2 of question 3, you're told that you have a bag with a very large number of wooden tiles and that each tile has a letter and each letter has the same number of tiles. So I've condensed that information here where all the numbers are much greater than 1. They're all equal. And this is just something that will be used later where n total is equal to NA plus NB plus NC. And this will in total equal to 26 NA or N anything. Let me rewrite that. Yeah, okay. So now you're asked for the probability of picking B and then E in that order. But after you pick a tile, you will not be able to replace it. So that turns into the first choice, you will have to pick B. So it's 1 over 26 because there's 1 over 26 of the tiles will be a tile with B on it. And the next tile, it should be you should have N total minus 1, but since, and then there should be 1 over here because and E over here. So this N total over 1, this should happen, but since we know that N total is 26 NA and NA itself is already much greater than 1, this N total is essentially still just N total. So you really have 1 over 26 times NE over N total, which is equal to 1 over 26 times NE over 26 NE, and then 1 over 26 squared. So for the second one, for part B, it's a similar question, except we can get them in any order. So that means you can either choose B or E first, and then just do the other letter for the second one. So that just really just means you have 2 choices for the first one and only 1 choice for the second. And following similar logic, you can just write it out as in this form, and you can calculate that. For part C, now you only have 4 tiles. So N total will only be 4 now, which is not much greater than 1. And for your first choice, this is also ordered where you have to pick B then C. So your first choice, you have to get B. So you have a 1 out of 4 chance. And then the next one, you have to pick C. So you have only 1 choice in the numerator, and this would be N total minus 1. But N total here is known and it's not much greater than 1. So you should be able to just plug it in and get an answer. And that will be all for question 3. Are there any questions? Okay, so Julian asked, can you explain why you approximated NRE and over NE minus 1 as the same? So here, it's not actually NE, this is N total. Let me write it to the side bigger. So this would be, it's that NE over N total minus 1. And N total minus 1, I approximate this as NE over N total because N total, as I wrote over here, is 26 of NA and N or any letter. And all of those numbers are much greater than 1 already. So when you add them together and you subtract 1, it doesn't make too much of a difference. So it won't change it. And we approximate it as just N total anyway. Okay. All right. And then I guess we can go to the next question now.
All right, I'll be doing question 4. Okay. All right, so question 4 is giving you a double helix that consists of 11 base pairs. And we're comparing the relative population of 2 different states. State A has all 11 base pairs formed, and state B has specifically base pair 5 and base pair 10 broken. And the energy cost for breaking one base pair is 1.25 kilojoules per mole. So first, to get the relative population, you can do this with the Boltzmann factor. As you can see here, the relative population of B and A would be equal to the Boltzmann factor. And now we'd have to consider the energy difference between the two states. So for state A, we can think of this kind of as a ground state with all the bonds are formed, so energy of A would be 0. And for B, it's 2 specific base pairs that are broken. So we can multiply, you can figure out the energy there, and then to get the change in energy, we'll take the difference, and that'll give you the relative population of B compared to A. And note here that in each state, there was one way each state can happen. Because now in question or part 2, it's basically the same question, except now for state D, any 2 base pairs can be broken instead of specifically 2 specific base pairs. So if we first look at the energies, we'll notice the energy difference is going to be the same as the previous parts, because in each instance, C will clearly be the same, have all base pairs formed. And for D, in each given microstate, there'll still be 2 base pairs broken. So now what we'd have to consider is the number of ways each state can happen, and that'll contribute to the relative population. So for state C, there is one way it can happen, because there's only one way that you can have all the base pairs formed. But for state D, we can find the multiplicity or number of ways that any 2 base pairs in an 11 base pair helix can be broken. And we can use this multiplicity formula for the combinations. And you can set M equal to the total number of base pairs in a helix, and N to the number of base pairs that are going to become broken in any given way that state could happen. So that would be any 2 base pairs. And then that would give you the number of ways that any 2 base pairs can be broken in that helix. So now we can go back to the relative population equation, and we'll see that the energy term to the right will be the same, as you can see here. And now we'll have to factor in the ratio of the number of ways it can happen. So we plug in the number of ways that state D could happen compared to the number of ways state C could happen, which would just be 1. And then state D would be, there's more than one ways state D would happen. So overall, that would, once you plug it in, you'll see that that'll increase the relative population of state D compared to C, compared with part 1 where it was B to A. And yeah, that wraps it up. Does anyone have any questions? All right.
Just one quick question.
Mhm.
In that equation, what does M and N represent again?
Yeah, let me pull it up. Yeah, so M would be the total number of base pairs that could possibly be broken. And then N would be the number of base pairs that that become broken. So there's 11 total base pairs, and 2 of them can become broken in any given state of D. So N would be 2 and M would be 11. Does that make sense?
Yeah, thank you.
All right, I think that's the last question for this section.